it splits into two subsections. So one section is target paper class. Target paper class. It's online. Online and physical both, okay? Target paper class. Now, other section of this paper class is section-wise past paper discussion. Section-wise past paper discussion, we say that SPD sessions. Section-wise past paper discussion. A short term is SPD. SPD. Now, mainly in target paper class, we do the papers, right? Currently, we do papers by keeping 1.5 hour time, right? Then every 2 consecutive weeks, we do MCQs. The next 2 consecutive weeks, we do essay papers. That's how this target paper class is going, right? First important thing you should understand in this target paper class, we don't put past paper questions to these papers that we give in this target paper class. This target paper class, all the papers are prepared considering if we're taking model paper questions, right? All the school term test papers and so there are more model papers. So we take questions from them, and so we prepare this target paper class. Talking about the section-wise past paper discussion sessions, mainly my intention is to cover all the MCQs, structured essays and essay questions from 1990 A levels to 2022 A levels. It's very big. My plans to discuss very big number of questions we are going to do under this section. The plan is to discuss all the MCQ, structured essays and essay questions from 1990 A levels to 2023 A level past papers. Past papers. Every week you will get one target paper, right? Now currently today we are discussing target paper 4. Then you are getting target paper 4 and you get answer book for every target paper. Because in the discussion session, that means today, every discussion session, whatever I explain the board, so you should write in that answer book. Then you get target paper every week and an answer book every week. In addition to that, I mentioned that we are doing SPD session as well. You will get every week one SPD paper. That SPD paper contains past paper, MCQs, essays. Now I have uploaded SPD2 paper in the platform, right? Then suppose if we discuss essay papers, in addition to target paper, answer book, SPD paper, you will get marking scheme as well. Now currently I didn't upload marking scheme for target paper 2, so target paper 4, but I will upload as soon as I finish this session, I will upload the marking scheme as well, right? Then that's the plan. Uh, this is the idea of 24 paper class. It divides into two subsections, target paper class and SPD section-wise past discussion. We discuss model papers, model questions in target paper class by keeping time. When it considers section-wise past discussion, section-wise, for an example, rotational motion, we take all the past paper MCQs. Then we discuss all those MCQs related to rotational motion. Then you can revise whatever you learned before. Then today SPD paper is about work energy power. Then I have taken past paper MCQs and essay from work energy power section. So when I discuss that, you will be able to understand. You will be able to revise things. That's next important thing. Online class, we do this target paper class Sunday. We start discussing the target paper Sunday 7 p.m. onwards. 7 p.m. onwards we discuss. Right? But section wise pass for discussion, I have given 2 days, Tuesday and Wednesday, from 10:30 p.m. Sometimes I don't do Tuesday and Wednesday both until I complete that SPD paper given in that week. I will do. So therefore, you roughly, if you understand, usually we discuss section wise pass for discussion every Tuesday or Wednesday from 10:30 p.m. onwards. Tuesday, Wednesday, 10:30 p.m. onwards, right? So then we can assume that now we have around 10 months to have our A level exams, 24 level exams. We have around 10 months. So already 4 papers discussed. My plan is to discuss 50 target papers at least. At least discuss 50 target papers. In addition to that, to complete all the past papers from 1990 to 2023. It's a big thing. It's a big thing, right? Now, currently in the target papers, we do 2 structured essays, 2 essays, and MCQs. There are 35 MCQs. But upcoming days, upcoming months, we increase number of questions in the paper, right? Okay, that's kind of explanation about how this paper class going on. Because some students they don't know that, so that's a kind of understanding I provided. Okay, we'll start discussing target number 4, right? Okay, right. Okay. Now, if you notice any kind of connection issues or anything, let me know. Right. Give me a second. Right. Yes. Give me a second. Right. I will discuss. A part A, structured essay, question 1. Right. Okay. Target paper 4. Right. Yes. Part A, question number 1. Part A, first question. Right. The diagram shows a student sitting on a table, rotating about the vertical axis through its center. It is not anis, it should be vertical axis through its center. The rotation speed is displayed on a computer screen. Initially, she is stretching arms forward as shown in the figure. Then the movement of inertia, it's not movement of inertia, it should be moment of inertia. Of the table with the student is 4.1 kilograms m squared. And the speed of table is 2.7 radians per second. 2.7 radians per second. Simply find the angular momentum of the table with the student. Find the angular momentum of the table with the student. Now, angular momentum, rotational motions, the very important theory concept is angular momentum. I explained two important equations to find the angular momentum. The most popular equation is angular momentum is equal I omega. Angular momentum equals I omega. Rotation of angular momentum is capital L. Capital equals I omega. I means moment of inertia of that rotating system. Omega means angular velocity of the system. This is the most popular equation to find the angular momentum. But you need to understand there is one more equation to find the angular momentum. That is mvr, mass tangential velocity into the distance to that point from the axis of rotation. These are two important equations. So usually when I explain something, I revise all the important theories also. That's how this discussion going. Yes. Now they have given a girl with the table rotating. Now she has stretched, if not, she has extended her hands and she's rotating on a table. Right. Stretched hands. Let's say this is our axis of rotation. If we assume this is our axis of rotation, let's assume she is rotating in anti-clockwise direction. Rotating in anti-clockwise direction. They mentioned angular velocity of the girl with the system, girl with the table. This time my rotating system is girl with the table. Angular momentum is they have given how much 2.7 radian per second. I say omega 1. Omega 1 is given as 2.7 radian per second. And also they mentioned when she has extended, when she stretched her hands, and when she is rotating, moment of inertia of the system is how much? 4.1. I say moment of inertia I1 is 4.1 kg m squared, right? But simply they are asking find the angular momentum of the table with the student, the equation L equals I omega equation. Simply, if I apply L equals I omega equation, then I want to find capital L. I want to find L. Then L equals I means moment of inertia. That is how much 4.1. Angular velocity omega will be 2.7. Then when we simplify this, we are getting L. L equals. We are getting L equals. If I multiply 4.1 and 2.7, I am getting that. I am getting 11.07. 11.07. 11.07. But you must remember the units, right? Kg Mass is measured in kilograms kg. Velocity means m is minus 1. Distance meter kg m square is minus 1. Simply done. Simple with asking define the angular momentum of a particle in 2 wax. That's a small printing mistake. It must be corrected as define the angular momentum of a particle. Please cut that in 2 wax. Please cut it. Define the angular momentum of a particle. Now, how did we learn angular momentum? Angular momentum means understand the torque of linear momentum around an axis of rotation. One last time I said that the torque of linear momentum of a particle around an axis of rotation. So therefore, you should write down angularly simple B. Simple B. Let's say this is my axis of rotation. Now this simple limb particle at this instant its tangential velocity is V. The perpendicular distance to the simple limb particle from the axis of rotation is simple r. Then we define angular momentum as the torque of linear momentum of a particle about an axis. That means we can write down angular momentum L equals torque of linear momentum. Linear momentum means capital P into perpendicular distance. That is simple R. Therefore, angular momentum equals linear momentum means mass into velocity, simple R. But what you want to write is, you want to write down for simple B, the torque of linear momentum of a particle about an axis of rotation is defined as angular momentum. That's it. So that is what you should write down. Okay. Now simple C. Give me a second. Now simple C. The student, while rotating, picked an object of mass 2.5 kilogram at her hands, at her hand level as shown in the diagram. And now, girl with the table is rotating under angular velocity omega 1 2.7 radian per second. Moment of inertia of the girl with the table is how much? 4.1 kgm squared. Now, what she's doing now, she has picked a mass of 2.5 kilogram and she has kept that mass in this way. Now, she is holding some kind of mass 2.5 kilogram this way. Now that mass 2.5 kilogram, the girl and the table, entire system is rotating, right? Then they're asking the question, find the angular velocity of the system after that. Before she has that mass 2.5 kilogram, her angular velocity was how much? 2.7 radian per second. They're asking after she has picked that mass 2.5 kilogram, what is her angular momentum, angular velocity now? I want to find the angular velocity. Now simple C. Simple C. Now she is holding. Now if I consider this as my before scenario, before, before. Now after scenario, right. Now this time same, this is the axis of rotation. Now she has picked some kind of mass 2.5 kilogram. This is the mass. She is holding a mass of 2.5 kilograms. Now what would happen? Now we know that total moment of inertia will be different now. Previously, total moment of inertia I1 is 4.1 kg m square. But now total moment of inertia of the system is different, right? Then what happened to the moment of inertia of the system right now? Moment of inertia of the system has increased because now she is holding another mass of 2.5 kilogram. Now her total mass, total moment of inertia has increased. But understand, still there is no resultant torque acting on the system. If there is no, now what is conservation of angular momentum? Now I want to teach you what is conservation of angular momentum. It says that when you consider any rotating system, if there is no resultant torque acting on the rotating system around a particular direction, always, always, total angular momentum of the system is always a constant. Now, you need to understand, even she has picked that mass 2.5 kilogram, there is no resultant torque acting on the system. So therefore, I can say that always, even after she picked that mass 2.5 kilogram, that system's angular momentum must be a constant. That system's angular momentum must be a constant. Then I can apply conservation of angular momentum for this case. For C, Roman number 1, I can apply conservation of angular momentum. They're asking find the angular velocity of the system after that. I say after angular velocity is omega 2. I say now after moment of inertia of the system is I2. Then if I apply conservation of angular momentum, home, always angular momentum of the system is conserved. That means equal. Angular momentum before and angular momentum after system is always a constant. So therefore, I can write down I1 omega 1 equals I2 omega 2. I can write down I1 omega 1 equals I2 omega 2. I1 omega 1 equals I2 omega 2. I know I1 is how much? 4.1. Omega 1 is 2.7. I1 omega 1 means I know that 11.07. 11.07. I2. Now I want to find omega 2. How do I find I2? I know moment of inertia of the girl with the table is I know it's 4.1. Newly added one is that mass 2.5 kilogram. Right? It's by 2.5 kilogram. Mass is 2.5 kilograms. The distance to this mass from the axis of rotation is the distance to this mass from the axis of rotation is they have given in the diagram 0.6 meters. This distance 0.6 meters. 0.6 meters. Then we want to assume in this case, one assumption is now we need to assume this mass as some kind of point mass. If you assume this mass is point mass, what is the equation to find the moment of inertia of a point mass? I equals mr squared. I equals mr squared. That's an important point, right? I equals mr squared equation. Then I can find now total moment of inertia of the system is now total moment of inertia of the system is 4.1 plus 4.1 means moment of inertia of the girl with the table plus moment of inertia of that mass 2.5 kilogram mr squared. 2.5, the distance to the mass from the axis of rotation is 0.6 square into omega 2 into omega 2 into omega 2. When I simplify this, if I subject omega 2, I am getting my omega 2 will be equal to exactly will be exactly equal to 2.3, around 2.3 radians per second, around 2.3 radians per second, rad per second. See, Roman number 1 is discussed. Roman number 2, write down the principle applied for the above calculation. Write down the principle applied for the above calculation. That is conservation of angular momentum. We applied conservation of angular momentum. So Roman number 2, you want to write down conservation of angular momentum. Conservation of angular momentum. Angular momentum. Now, you should define that what is conservation of angular momentum. You have to write on the definition also. Now, what is conservation of angular momentum? Any rotating system, if there is no resultant torque, acting on any rotating system around an axis, through that axis, the rotating system's angular momentum is always a constant, right? That's the idea of that. Yes. Now, next one. Problem number 3. Now the student folds her arms, closing the object towards her body. Now the student folds her arms, closing the object towards her body. Explain what happened to the speed of the system, giving reasons. Now what would happen? Now just think about this diagram. Now this girl is holding this mass 2.5 kilograms. What would happen when she folds her arms? When she folds her arms and when she brings that mass 2.5 kilogram towards her body, what would happen for the mass distribution? What would happen for the mass distribution? Comparing with mass distribution on this diagram, when she extended her hands and while she is holding the mass and when she is rotating, that mass distribution is larger than mass distribution of the system when she folded her hands. When mass distribution becomes low, what can you say about the moment of inertia? I told you, always understand this important point. Mass distribution is one of the factors on which moment of inertia depends. If mass distribution becomes low, moment of inertia of the rotating system also becomes. Do you understand? When she folds her hand, what would happen? Her mass distribution becomes low. As a result, what can you say about her moment of inertia about this axis? It also becomes low. As a result, but always we know that the system must maintain constant angular velocity. Why? Because still there is no resultant torque acting on the system. So what she has done is, initially she has extended her hands. Now she just folded hands. So during that process, there won't be any resultant torque acting on the system. Then always angular momentum must be constant. Even she folded her hands by bringing the mass towards her, total moment of system, total momentum, angular momentum of the system must be a constant, right? But what happened? What happened? Roman number 3. We know L equals I omega equation. According to L equals I omega equation, L is always a constant. Even she extended her hands or even she folded hands, moment of inertia must be constant. Why? There is no resultant torque acting on the system. Now what happened to Y? When she has folded the hands, I decreased. I decreased. Then what would happen for the angular momentum of the system now? It must be increased. It must be increased. Angular momentum must be increased. Then they're asking now the student folds her arms closing the object towards her body. Explain what happened to the speed of system by giving reasons. So what happens when she folds her arms by bringing 2.5 kilogram towards her body? Mass distribution of the system becomes low. As a result, moment of inertia around that axis of rotation becomes low. Always, angular momentum is constant if there is no resultant torque. In this process also, there won't be resultant torque acting on the system. Therefore, even now, angular momentum of the system must be constant. When I decreases relatively, Angular momentum must be increased. Therefore, angular velocity of the system is increased. That's what you want to write down in that example, that question. Next, they are asking, problem number 4, while rotating as in part C, suddenly the object falls from her hand. What is the angular velocity of the system? What is the angular velocity of the remaining system in the subsequent motion? Right. Now I found that we found when she has extended now, as shown in the figure C, means this is the figure C. Now this girl is rotating by extending her hands and by holding this mass 2.5 kilogram. She's rotating. She's rotating. Now what would happen when suddenly this 2.5 kilogram mass uh, fell down? This 2.5 kilogram mass falls down. What would happen? L is always a constant. Angular momentum is always a constant. Now what would happen? When when this 2.5 kilogram mass falls down, then the system will be converted to this system. Then what can you say about the angular velocity of the system now? 2.7 radians per second. So therefore, Roman number 4 answer is 2.7 radians per second. Omega 1, that is 2.7 radians per second. Radian per second. Then simple D Roman number 1, simple D Roman number 1. Simple D Roman number 1. In here, in another experiment using the same setup, the table with the sub student is rotating with angular velocity 1.5 radian per second. The table with the student rotating with angular velocity 1.5 radian per second. Now she put down her one leg to touch the ground. What would happen now? The girl with the table is rotating with an angular velocity of 1.5 radian per second. What would happen when she touches the ground by her leg? Then from that instant onwards, what would happen? There will be kind of resistive torque acting on the rotating system. Am I correct? I think you might have this experience, right? While you are rotating, if you put your leg and if you touch the ground, what would happen to your rotational motion? It will retard. So now what will happen when the moment she touches her leg on the ground, from that instant onwards, there will be kind of resistive torque acting on the system. As a result, the rotating system will retard and will become zero angular velocity at the end. Okay. Due to the frictional torque from the ground, the table comes to rest in 0.75 seconds. The moment of inertia of the system is 4.5 kg m squared. Calculate angular retardation. That means we need to find the angular deceleration, right? If I say this rotating system as like this, let's assume this is my rotational system. Just assume this as my rotational system. Then, if we assume the system is rotating in clockwise direction with an angular velocity of 1.5 radian per second, 1.5 radian per second. Now, what happens when that girl touches the ground by her leg? There will be some kind of resultant resistive force acting in the opposite direction of rotation. This is my resultant resistive torque acting on the system. Initially, the system was rotating in clockwise direction. When the moment she touches the ground, from that instant onwards, there will be some kind of resultant torque acting on the system in anti-clockwise direction, if not opposite direction of rotation. As a result, there will be some kind of deceleration in anti-clockwise direction. Okay, right. After 0.75 second later, now here time is 0. After 0.75 seconds later, now time is 0.75 seconds. Now what would happen? Entire system comes to rest. That means now angular velocity will be 0. Now angular velocity will be 0. Omega equals 0 radian per second. They are asking what will be the angular retardation. That means we want to find angular deceleration. Now, how do we find this one? We can use what equation? What is the equivalent angular velocity equation for v equals u plus at linear motion equation? That angular motion equation will be omega equals omega naught plus alpha t. So I can apply that equation. Omega equals omega naught plus alpha t. What direction? In the clockwise direction, right? So then I can write omega equals 0. Final angular velocity is 0. Initial angular velocity omega naught will be 1.5 plus angular deceleration. I say angular acceleration as simple t. Here alpha means always angular acceleration into time taken is 0.75. Then if I subject alpha, I am getting my alpha equals 1.5 over 0.75. That means exactly minus 1.5 or 0.75 minus 2 radian is minus 2. So therefore, minus 2 means angular deceleration. You got it? Then I found simple D Roman number 1. Simple D Roman number 1, we found the answer. Simple D Roman number 2. Then they are asking, frictional torque. We want to find the torque produced by the resistive force. We can use what equation? We can use tau equals I alpha equation. If you want to find the resistive torque, I can use tau equals I alpha equation. So this is also one of the important equations in rotational motion. Tau equals I alpha equation. Tau equals I alpha equation. Right? Tau equals I alpha equation. Now I want to find the frictional torque. If I say frictional torque as tau equals moment of inertia around that axis of rotation is they have given 4.5. 4.5 angular acceleration. Here alpha means always angular acceleration. I found my angular acceleration as minus 2. I put minus 2. Then I am getting resistive torque will be 9 minus 9 rad s minus 2. Now some people you might have a small doubt regarding why minus. Minus is not compulsory. In case, what is the meaning of minus 2 radian per second? Minus 2 radian per second means what? Minus 2 means in that direction there is, now here I consider clockwise as positive. Clockwise direction is positive, anti-clockwise direction is negative. So if I get minus, what is the meaning? Anti-clockwise direction. Then acceleration is acting in anti-clockwise direction. Then clockwise direction there is deceleration. Likewise, I'm getting torque as minus 9. Minus means anti-clockwise. Anti-clockwise direction torque is 9. This must be Newton meters. 9 Newton meters. Then first structure say question is completely discussed. I hope you guys understood what I explained. Now we'll go to second structure say question. Structure say question number 2. Right? The practical done to find the density of kerosene is also provided below. U-tube mounted on a vertical frame of suitable scale, amounts of oil, kerosene required, funnel. Simply, problem number 1, draw a label diagram of the practical apparatus showing clearly the levels of water and kerosene stems and their common interface. If I draw that, right, right. right? Draw a label diagram of the practical apparatus showing clearly the levels of water and kerosene stems and their common interface. Now, generally we do the YouTube practical considering water and coconut oil. What can you say about the densities of coconut oil and water? We know coconut oil density is smaller than density of water. Very simple to understand. When you compare kerosene and water, kerosene means it's bhumitil, right? Density of kerosene is lower than density of water. Do you understand? First important point is density of kerosene is lower than density of water. Then, how would be the apparatus? If I draw the apparatus, Roman number one. Then, then you need to understand if you want to get marks, if you assume this level as common interface, this is common interface, common interface. You should mark now. This red color liquid column is my kerosene liquid column. Kerosene, kerosene, kerosene. This blue color liquid column is my water column. It's water, water, right? You will get the marks. Then understand about the height of the columns, about the common interface, the height of the water column, and about the common interface, the height of the kerosene column. You should have marked the height of the kerosene column above the common interface larger than the height of the water column above the common interface. Always understand water column height must be smaller than height of the kerosene column. More commonly, if I say that, always understand when you mark liquid columns in the YouTube, the liquid which is having larger density, liquid which is having larger density, in this case water, having larger density, liquid which is having larger density should have smaller height of the column above the common interface. Above the common interface, liquid with the larger density should have smaller height. Above the common interface, liquid with the smaller density should have the larger height, right? That is one important thing. Then if you have marked this common interface correctly, in addition to these liquid heights and mentioned by, you have to mention kerosene and water. Then you should mark this common interface. In addition to them, you have to mark that scale. You have to mark the scale. You have to mark the scale. The scale. So in this side also there's a scale. I think up to now everything is very clear. So then you will get the right marks. Marking scheme will be uploaded after the session completely discussed. So then you can go through the marking scheme and you can check for which steps. So you will be given marks, right? Yes. Problem number 2, mark the two measurements you want to obtain as H1 and H2 in the above drawn figure. Now, as they haven't detailedly mentioned which is water column height and which is kerosene column height, you can consider H1 as water column height above the common interface. If not, you can consider H1 as kerosene column height above the common interface. It's up to you, but I consider H1 as kerosene column height and H2 as water column height. I consider in that way. H1 is my kerosene column height. H1 is kerosene column height. My H2 will be water column height. H2 will be water column height. Then if you have marked these H1, H2 heights in the relevant columns, you will get 1 marks. Simple B, if the densities of kerosene and water are D1, D2. Densities of kerosene and water are D1, D2. Density of kerosene, that is D1. Density of water, that is D2. Density of water, that is D2. Then they are asking, write an expression for D1 in terms of D2, H1, H2. Simple B. Simple B. Simple B. Now what can I do? Now very important theory point. Important point you should notice, you should write down in your review book. First important thing is, in hydrostatics we learned that in a stationary, incompressible, non-viscous liquid fluid, when you consider all the liquid particles in the same horizontal level, very carefully listen again. In a stationary, incompressible, non-viscous fluid, liquid particles at the same horizontal level have same total pressure. Am I correct? Now I'm going to take 2 points. I'm going to consider 2 points in the water. In the water, exactly at the common interface. If I say point capital A, point capital A is here. This will be my point capital B. Point capital B. Then this point capital A, point capital B, both are in the water exactly at the common interface. Then I can say point A and point B both are at the same horizontal level. Then we learned a law that if you select if the liquid particles, if the points are in the same liquid in the same horizontal line, then their pressure must be equal. Total pressure at A must be equal to total pressure at B. That is important condition. then I can say that PA equals PB. I hope you guys know the reason why PA equals PB. I hope I explained right now why they are equal. Now I can write down pressure at point A is because of the pressure produced by the water column above the common interface and the atmospheric pressure 5 and the atmospheric pressure 5. Pressure at point capital B is because of the pressure produced by the kerosene column and the atmospheric pressure 5. How do we find the pressure of hydrostatic pressure? How do we find the hydrostatic pressure of a liquid column? If there's a liquid column of height simple h and density rho, how do we find the hydrostatic pressure of liquid column? H rho g equation. I think you can remember. So then I can write down pressure at point A equals pressure produced by the water column H rho g, that means H2 D2G, H2 D2G plus atmospheric pressure 5 must be equal to pressure produced by the pressure at point capital B, pressure produced by the kerosene H1 D1G, H1 D1G plus 5. 5. So then we know this 5 and 5 get cancel out, G cancel out. I can write down H2 D2 equals H1 D1. Now I need to find, they're asking write an expression for D1 in terms of D2 H1 H2. Other I want to subject D1. I want to subject D1. I want to subject D1. If I subject D1, I'm getting D1 equals H2 H1 D2. That's done. Simple C, Roman number 1. If D1 is to be determined by drawing a graph, if D1 is to be determined by drawing a graph, which liquid column is chosen as the independent variable? Okay. Then simple C, Roman number 1. Simple C, Roman number 1. Now can I remember now? Now basically we do this YouTube practical to determine the relative density of a liquid. Now here we poured water and kerosene. Then our main goal is to determine the relative density of kerosene. Now usually we find the relative density by using graphical method. Why? I told that why we always going with graphical method to find the relative density. Why we always take many readings and why we always go with the graphical methods to find the relative density. The reason is now one can now rather than taking many readings, one can take only one reading and based on that they can find the D1 density. If one can measure H1, H2, and if now D2 means density of water, then one can easily find the relative density of the liquid that we want to find. But why we always go with graphical method? The reason is when we go with a graphical method, we can minimize the errors that we do during a practical. That's why we are always going with graphical method. If you are going with graphical method, somehow we need to plot a graph. In a graph, there is x-axis, there is y-axis. That means x-axis means independent variable. I hope you guys know. Y-axis means dependent variable. Now, we want to change one parameter. Based on that, another parameter must be changed. Then here, what should we consider as x and y-axis? Obviously, length of the columns, right? If I add more oil or more water, then we can change the height of the liquid columns. Then exactly which height of the liquid column that we consider as x-axis, which height, if not which column that we consider as our y-axis. Now there are two heights in H1 and H2. H1 and H2. My question is, which height of the liquid column that we consider as our x-axis, which height of the liquid column that we consider as y-axis? I told you in the practical that when we were discussing, I told you that always understand if it is a YouTube practical, always your x-axis must be, if not independent variable must be height of the uh, coconut oil column. In this question, height of the kerosene column. Always select, important point, always select the height of the liquid with low density as your independent variable. Then what will be your dependent variable? Height of the high density liquid. In this practical also we select kerosene is low density liquid, therefore we consider height of the kerosene column as our independent variable. In this case also my x-axis will be height of the kerosene column. Height of the kerosene column is h1. My y-axis will be height of the water column. Always your x-axis must be height of the low density liquid. Your y-axis must be height of the high density liquid. Why? Now, see Roman number 1, they are asking if D1 is to be determined by drawing a graph, which liquid column is chosen as the independent variable. Obviously, our independent variable, if not our x-axis, must be the height of the kerosene oil column, kerosene column. Roman number 2, they are asking what is the reason why the other measurement, that means H2, height of the water column. What is the reason why the other measurement is not chosen as independent variable? Explain the reason also in the practical. Why? Now we know that. Now why we now what is our intention? We change we change height of the liquid columns and we obtain 6 readings, right? If I say x-axis is h1, y-axis is h2, we obtain 6 coordinates of h1, h2. We obtain 6 coordinates of h1, h2. Then only we are able to plot a graph. Somehow we want to change, we want to obtain different heights of kerosene column above the common interface and different heights of water column above common interface. Now what would happen if you select your x-axis as water column height? The problem is no matter how much you add water, what would happen? No matter how much you add water, by expecting changing the heights of the column above the common interface, understand, no matter how much you add water, height of the columns above the common interface will not change. No matter how much you add water, height of the columns, water and kerosene above the common interface will not change. If not in other way, I can say that no matter now, when you add more and more water, what would happen? We are expecting H1, H2 will be changed, but what will happen? No matter how much you add water, what will happen? The common interface will rise. That's what's happening. Now, when you add water, if not when you add high density liquid, that means if you select your x-axis as independent variable as high density liquid column height, no matter you change your height of the high density liquid column, there won't be any change no matter how much you add high density liquid, there won't be any change about the common interface in the liquid columns. That's the reason why we select our x-axis as height of the low density liquid. Do you understand? I explained these things in the practical detailing. Then see Roman number 1, Roman number 2, I think we discussed. Then Roman number 3, there's Roman number 3 as well. There's Roman number 3 as well. Roman number 3 says what? The gradient of such a graph is found to be 0.86. Determine the density of kerosene. Density of water is 1000 kg m minus 3. Now Roman number 3. Then now we understood x-axis must be height of the kerosene column, y-axis must be the height of the water column. Now we understood. Now this is the equation. This is the equation. Now y is h2, therefore I thought of subject h2 from this equation. Then I get that h2 equals. Then I get h2 equals d1 over d2, d1 over d2 dot, d1 over d2 dot h1. Then what is my h2? H2 is my y-axis. H2 is my y-axis. H1 is my x-axis. d1 over d2, that is my gradient, y equals mx graph. Then when I plot the graph, the gradient represents d1 over d2. Gradient is d1 over d2. They have given that gradient is 0.86. That gradient is 0.86 equals to d1 over d2. I think I want to find d1. d1 means density of kerosene. I think I want to find d1. I want to find d1. If I subject d1, I am getting d1 equals 0.86 into density of water 1000. Therefore, I am getting 860 kg m minus 3 as the density of the kerosene. D1. Okay, here D1 means 860 kg m minus 3. So then, right? Then, uh, simple C done, simple D. Simple D. In such a practical, which liquid should be poured first in the YouTube? Give reasons for your answer. Now, now always understand when you do this YouTube practical, the liquid having larger density must be poured at first. Then only gently be at liquid with small density, right? In such a practical, which liquid should be poured at first in the YouTube? Always we should pour liquid with larger density at first. Give reasons for your answer. What would happen if I pour low density liquid at first and if I pour large density liquid at the second? For an example, let's say initially I poured kerosene. Now initially I poured kerosene. Now initially I pour kerosene. Then kerosene has filled up to this level. Now I'm adding high density liquid water. Now I'm adding high density liquid water. Then what would happen? The water is having high density. What would happen? This water will go through the kerosene because water has large density. Therefore, what would happen? This water will go through the kerosene and deposit at the bottom of the YouTube. As a result, what would happen for your low density liquid? Your low density liquid will separate into two columns and remain in both the columns. Do you understand? Then what will happen? As a result, what will happen? Water has large density, therefore it always deposits at the bottom. Now what would happen? That kerosene column will be divided into both the arms. Then we come to the practical. That's the idea. Uh, right. Then simple D also done. Simple D also done. Then simple E. Why is the above method not suitable for determining the density of a copper sulfate solution? Now, what is the when you consider coconut oil and water? If not, when you consider kerosene, kerosene and water, they are not miscible with each other. In other words, if I can say that kerosene and water, they are immiscible. They do not mix with each other. What can you say about copper sulfate solution and water? Copper sulfate is miscible with water. Then we'll be able to maintain copper sulfate solution column and water column separately in the YouTube. We are not able to do that. So therefore, understand why is the above method is not suitable for determining the density of a copper sulfate solution. The reason is they are miscible. Therefore, we can't maintain copper sulfate solution column and water column separately. That's the reason. They are miscible. Suggest another method for it. Hair apparatus. I think if you can remember why we used hair apparatus. By using hair apparatus, we can measure relative density between two miscible liquids, copper sulfate and water, and two immiscible liquids as well. Do you understand? If we use hair apparatus, we can use we can use to find the relative density between two miscible liquids, if not two immiscible liquids. But if you are using water, sorry, if you are using YouTube, you can measure mainly the relative density between two immiscible liquids. But when you use hair apparatus, even though they are miscible or immiscible, we can use to determine relative density of both liquids. That's the idea. Then structure one and structure two completely discussed. Now we have two essay question to discuss. Right. The third one is about Doppler effect. Mm, I thought of discussing fourth one, question number 4 first, and then I will discuss third one later. Right. So we'll take a 5 minute break. Sorry, we'll take few minutes. Mm, right. Give me a second. All right. Then we'll discuss question number 4. Right. Right. Now state the Newton's second law. Question number 4. State the Newton's second law. When there is no resultant force, if not we can say when there is no external unbalanced force acting on a system, right? Sorry, Newton's second law. Always understand if there is external unbalanced force acting on a system, if there is external unbalanced force acting on a system, that external unbalanced force, if not that resultant force, always directly proportional to rate of change in linear momentum. Do you understand? Newton's second law says that resultant force acting on a system always directly proportional to rate of change in linear momentum. Then for Roman number 1, simply Roman number 1. Question number 4, simple A, Roman number 1. Newton's second law. Newton's second law. External now. If I say this is my system, external force acting on the system, I say capital F. External force acting on the system is capital F. Right? Because of this capital F resultant force, obviously what would happen to the system's momentum, linear momentum? Linear momentum must be changed. Linear momentum means we know that at a particular instant, mass of the object into that instant's velocity, that's what we call as linear momentum, m into v. So when there is a result force acting on a system, we know that velocity of the object changes with the time. If velocity of the object changes with the time, we know that linear momentum also changes with the time. Am I correct? Then Newton told that if there is a resultant force acting on a system, that resultant force directly proportional to rate of change in linear momentum. Capital F equals rate of change in linear momentum. Linear momentum means P, change in linear momentum is delta P, rate of change in linear momentum is delta P over delta T. Right? This is what Newton told in his second law. But you should understand some important points. First important thing is you want to know that what is this linear momentum. Linear momentum means capital P means mass into velocity. Linear momentum capital P means mass into velocity. Okay. It is defined as mass into velocity at a particular instant. Mass into velocity. Right. And we know when there's a resultant force, I take two different instances. For example, if I say t equals 0 and if I say t equals simple t, if I consider two different instances, t equals 0, now t equals simple t. Resultant force acting on the system throughout this motion is capital F. Resultant force capital F. Now I'm just revising important things. Now, what can I say about the velocity of the system? Every instant different. If I say when t equals 0, velocity of the system is v, sorry, u. When t equals 0, velocity of the system is u. Then I say when the time is simple t, velocity of the system is v. V. Right? Okay. And now what can I say about the linear momentum? Due to this resultant force, linear momentum changes. If I say mass of the system is simple limb, mass of the system is simple limb, but give me a second. Yes. Now I think you guys can hear what I'm speaking, right? But then we know that when t equals 0 and t equals simple t, we know linear momentum is changed. What is the linear momentum at this instant? M into u. If I say mass is simple limb, give me a second. Right. Can you hear me? Right. If I say mass of the system is simple limb, linear momentum before, I say P1, linear momentum before is P1, that is simple limb into U. Now I just revise it because this knowledge is important when I'm discussing that next idea, right? Right. Then when the time is t, when the time is t, linear momentum is m into v. Then how do you find the change in linear momentum? Because everything is important. That's why I just thought to revise this one. How do you find the change in linear momentum? Delta p. Delta p means we know that final linear momentum p2 minus initial linear momentum p1. That means mv minus mu delta p. Delta p means change in linear momentum. So what is this rate of change in linear momentum? Rate of change in linear momentum means delta p over delta t. Important thing, rate of change in linear momentum means rate of change in linear momentum means delta p over delta t. This knowledge is important when we do the upcoming questions, right? Yes, okay. Now we'll go back to the question. Then for Roman number one, state the Newton's second law. Yeah, I explained. Roman number two, a car moves from rest with uniform acceleration for 4 seconds and acquires a velocity 8 ms minus 1. If the resultant force applied to the car is 2000 Newton, resultant force applied to the car is 2000 Newton, what is the mass of the car? Mass of the car. Roman number two. Roman number two. Right? That's a car. Initial velocity of the car is 0. Within 4 seconds, velocity of the car is 8 ms minus 1. 8 ms minus 1. Time taken to obtain 8 ms minus 1 velocity from the initial point is 4 seconds. Time is 4 seconds. Resultant force acting on the car. Resultant force acting on the car is they have given. Resultant force is how much? Capital F is 2000 Newton. Resultant force is 2000 Newton. Capital F is 2000 Newton. What is the mass of the car? Now, mass, if I want to find the mass, if I know the resultant force, F equals ma equation. F equals ma equation, I can find the mass of the car, but I want to know the acceleration. If I consider linear motion, initial velocity u is 0, final velocity v is 8, time simple t is 4. I can find the acceleration by applying v equals u plus at equation. V equals u plus at equation. Roman number 2. I can apply in the direction of motion. V equals u plus at. Final velocity is 8. Initial velocity, that is how much? 0. Acceleration, I say simply. I want to find the time simply. Time is given as 4. Then acceleration of the car simply will be 2 ms minus 2. 2 simple ms minus 2. But we want to find the mass of the car. Resultant force acting on the car is 2000 Newton. If I apply F equals ma in the direction of motion, if I apply F equals ma, then resultant force acting on the car is 2000. I want to find the mass of the car simple limb. Mass of the car simple limb. Acceleration is 2. Then I can obtain mass of the car is 1000 kilograms. Mass of the car is how much? 1000 kilograms. Simple limb equals 1000 kilograms. Discussed. Roman number 3. If the air resistance on the car remains constant at 800 Newton, frictional force at 200 Newton, air resistance 800, frictional force 200, what is the force exerted by the engine? Now you should understand that this 2000 Newton acting on the car, that is the resultant force acting on the car. Resultant force acting on the car is 2000. Right? Roman number 3. If I do the car, resultant force acting on the car is 2000 Newton. Resultant force. They mentioned that there are air resistive force. We know air resistive force. Therefore, it is always in the opposite direction of motion. What is the magnitude of air resistive force? 800 Newton, opposite to the direction of motion. This direction, 800 Newton air resistive force. I say Fa, 800 Newtons. Frictional force, that is also acting opposite to the direction of motion. F, that is how much? 200 Newtons. But you need to understand this car is the resultant force acting on this car is 2000 Newton. Now we know there are two forces, air resistive force 800, friction force 200. then there must be a force exerted by the engine in the forward direction, right? I say force exerted by the engine, Fe. The resultant of force exerted by the engine, Fe, Fa, Ff. Resultant of these three forces is this 2000 Newton. Because you want to understand, if this car is moving, somehow there must be a force acting forward direction. That car is moving further, that car is accelerating, there must be resultant force forward direction. Force exerted by the engine acting forward direction. There are two resistive forces, friction force and air resistive force, backward direction. Resultant of these three forces is the 2000 Newton. Then I can write down this 2000 equals, this 2000 equals, I can write down this 2000 equals, if not Fe, force exerted by the engine, minus 800 minus 200, minus 800 minus 200 must be equal to resultant force, that is how much? 2000 Newton. Therefore, if I subject force exerted by the engine, Fe equals 3000 Newton. 3000 Newton. That is done. The next one, problem number 4. How far will the car travel to stop if the air resistance and friction remain constant at the above values when the force applied by the engine is 0? Now, when engine is stopped, force exerted by the engine will become 0. If engine is stopped, force exerted by the engine will become 0. Then now, there are only two forces, they are resistive forces. Now, when the engine is stopped, Fe will be 0. Now there are only two forces acting on the car, 800 air resistive force opposite direction, 200 friction force opposite direction. Then what is the resultant force acting on the car now? 1000, backward direction of the motion. They are asking how far. Now, okay, Roman 4. Now the resultant force acting, now engine is switched off, therefore F is 0. And now resultant force acting on the car is 1000 newtons backward direction. Right? This car is moving with 8 ms minus some velocity. At this instant, this car is having 8 ms minus 8 ms minus some velocity. 8 ms minus some velocity. Resultant force acting on the car is 1000, opposite direction. 1000 newton. Now what will happen? This car will decelerate. Finally, velocity of the car will become 0. Right? So they are asking how far will the car move? They are asking the displacement. The final velocity will be 0, ms minus 1. Then I want to find the displacement, capital S. I want to find the displacement, capital S. That's my goal. Now, I know u 8 ms minus 1. I know v is 0. I want to find displacement S. I can find the acceleration, that means deceleration. If I apply F equals m, now I know mass of the car is 1000 kilograms. In the direction of motion, if I apply F equals m, F equals m, resultant force acting on the car is 1000 Newton backward direction. I applied F equals m right side direction. What is the meaning of that? Forces backward direction are negative, minus 1000. Minus 1000 equals mass is 1000. Acceleration, I say simple. Then I am getting acceleration as minus 1 ms minus 2. That means deceleration. I am getting acceleration as minus 1 ms minus 2. That is deceleration. But I want to find the displacement. So again, I consider linear motion. I consider linear motion. I consider linear motion, right? What equation? I know A, I know U, I know V. I want to find S V squared equals U squared plus 2AS equation. In the direction of motion, I'm applying V squared equals U squared plus 2AS equation plus 2AS equation. Then my V will be 0. My V will be 0. My U. What's my U? 8. 8 squared plus 2. Acceleration is minus 1. Displacement is so when I simplify this, I am getting my simple S is 64 over 2, 32 meters. 32 meters. S equals 32 meters. 32 meters. Then simple A section completely covered. Simple B is the important section in this question. In this target paper 4, the most important question is simple B. That's the important thing in this paper, because every paper I try to give a concept very important. Now in this paper I wanted to teach you this thing properly. Okay, briefly I will explain. Okay, briefly I will explain everything. Right, 8:45, 9:45. I think time is enough. We can stop. Okay. Helicopter is held in space by spinning the rotor at high speed, pushing a stream of air vertical downwards. As the airstream pushes downwards, an upward force is exerted on the helicopter. The helicopter rises with that upward force. The length of a rotor blade is 5 meters. The mass of the helicopter with passengers is 3,600 kilograms, and the density of air is 1.2 kg minus 3. Phi equals simple B. This is the important question in this simple B. Very, very important thing. That's helicopter. Now, first of all, we'll clarify the given data. Given data. Given data, they have given radius, if not length of the rotor blade. If I consider one blade, length of this rotor blade is how much? 5 meters. I consider length of the rotor blade as R, capital R. Capital R means how much? 5 meters. I know capital R is 5 meters. Capital R 5 meters. In addition to that, length of the rotor blade, they have given mass of the helicopter with the passengers, capital M. Mass of the helicopter, if I say capital M is how much? Capital M is 3,600 kilograms. Density of the air. Density of the air, they have given 1.2 kg M minus 3. Rho is how much? 1.2 kg M minus 3. Given data. Those are the given data. Yeah, those are given data. Now they are asking Roman number 1, calculate the minimum speed at which rotor must transmit the airflow downwards for the helicopter to barely lift off the ground. Barely lift off the ground. Now we'll understand what's happening here. Now we might have seen that helicopters, by rotating the rotor of the helicopter, we might have seen that helicopters, they stay in the air in equilibrium state. If not, we might have seen that helicopter is moving in upward direction, moving in the upward direction. Now, how this happens? Now we know that if we want to move upwards, there must be some kind of resultant force acting on us in the upward direction. Am I correct? The basic idea is if we move upwards, there must be some kind of resultant force acting on us in upward direction. Then only we will be able to go upward direction. Do you understand? The problem is how this helicopter obtains that upward force. Obviously, helicopter has a weight mg vertical downward direction. If I mark the forces on the helicopter, definitely weight is acting on the helicopter downward direction. Weight is acting on the helicopter downward direction, obviously. Weight acting on the helicopter mg downward direction. Capital mg. Right? Then we know somehow there must be a vertical upward force acting on the helicopter. Then only helicopter can move upwards. The problem is how this helicopter achieves that vertical upward force. Do you understand? Now, the best example I can give for this is now sometimes let's say now there is a small tapyak. Let's say there is some kind of wall. So the wall, some kind of tapyak. I don't know what to say. Some kind of wall. Right now, you want to see what's happening beyond that wall, but the height of the wall is exactly in your height. So if you want to see what's happening beyond the wall, what we usually do? So we put our hands on the top surface of the wall, and what we do? We just push the wall down. So when we push the wall down, automatically we move upward direction. So what is the logic effort concept behind that incident? We apply a force on the wall downward direction. According to this third law, every action has equal and opposite reaction. When I apply a force on the wall vertical downward direction, equal opposite force is acting on me in upward direction. As a result, I move upwards. Very similar concept is applied in here also. Now, when that rotor of the helicopter rotates, what it does now, around that rotor, air particles are surrounded around that rotor. When the rotor is rotating, this rotor pushes air particles downwards. When the rotor is rotating, this rotor pushes air particles downwards. Then every action has equal opposite reaction. According to this third law, every action has equal and opposite reaction. When rotor pushes air particles downwards, air particles also push the rotor upward direction. So that's how this vertical force exerted on the helicopter. Do you understand? The simple understanding is, simple idea is, rotor pushes air particles downwards, air particles push the rotor upwards. Then initially we can assume that air particles, now initially we can assume before the rotor rotates, we can assume that velocity of the air particles are zero. We can say these air particles are stationary. These are my air particles. They are at stationary condition. They are at rest. When t equals 0. When t equals 0, rotor is also not rotating. When t equals 0, air particles also at rest. When t equals 0. Now what will happen? Always understand, when this rotor is rotating with a velocity of b, right? When this rotor is rotating with a velocity of b, very carefully understand this tangential velocity. When the rotor is rotating with a velocity of b, the first assumption that you want to make is, now in some when we take a practical example to a theoretical question, we want to do plenty of assumptions. First assumption is, whatever the velocity of the rotor, air particles also obtain same velocity. When the rotor is rotating with a velocity of v, first assumption is air particles also start to move with v constant velocity down direction. When the rotor is rotating with a velocity of v, air particles also start to move in downward direction with same velocity v. That is your first important assumption, right? Then now you can assume that now rotor started when t equals 0, rotor started to rotate. Now air particles, all the air particles below the helicopter, below the rotor, all the air particles below the rotor started to rotate. Sorry, all the air particles below the rotor started to move vertically downwards with a velocity of v. All the air particles are moving vertically downwards with the velocity of v, right? Just think about one air particle. When t equals 0, this air particle was at this location. After simple t time later, we can assume when t equals 0. When t equals 0, we'll assume rotor is stopped, rotor is not moving, then air particles are stationary. When t equals 0, rotor is not rotating, therefore air particles are stationary. In the next instant, we switch on the rotor. Now air particles are moving with velocity v. When the time is simple t, when the time is simple t, these air particles have moved somewhere here. When the time is simple t, all these air particles has moved in this position. Then I told you that velocity of the, when t equals 0, these air particles are stationary. The next instant rotor is switched on, air particles obtain capital V velocity, and after simple t time later, these air particles have reached this point, this position. If I ask you that, what is the displacement traveled by these air particles within simple t time? What is the displacement traveled by this air particles in simple t time? We can assume air particles moves under constant velocity v downward direction. So therefore, I can apply S equals ut equation downward direction. If I apply S equals ut equation downward direction, it's very important question. S equals ut equation downward direction. Then I can find the displacement traveled by these air particles within simple t time. If I say simple lich, this height simple lich. If I say this height is simple lich equals velocity of the air particle v, time is simple t. Now v also I don't know. I want to find the question. V is what I want to find. I think the question. Velocity of the rotor. I told you the summary. If I summarize, wait. Velocity of the rotor is v. Velocity of the air particles moving downward direction also v. First important thing. When t equals 0, air particles are at rest. At the next instant, we switch on the rotor. Now air particles start moving with a velocity of v. Within simple t time, displacement traveled by the air particle is simple h equals v into t. Equation 1. Right. Okay. Then we can assume that this air column, because if I can assume air column of volume, the cylindrical volume of air column I can take, and I can think this way. Now I can think that this helicopter pushes within simple t time. I can think that this helicopter pushes this much of cylindrical air column down in direction, right? I can assume this helicopter with the rotor pushes this much of cylindrical air column down in direction. So therefore, helicopter produces a force on the air column, a force on the air column downward direction. That is, I say that Fh. When helicopter produces a force on the air column downward direction, every reaction has equal opposite reaction. Air column also produces a force on the helicopter upward direction. That is that vertical force obtained by the helicopter. Now I think you understood how this vertical force exerted on the helicopter. The basic understanding is, if you think helicopter and the air column as two different objects, while by rotating the rotor, helicopter produces a force on the air column downwards. According to this third law, every action has equal opposite reaction. Therefore, air column also produces a force on the helicopter upward direction. Because of this Fh force, helicopter moves upwards or something else. Right. My target is finding the velocity of the rotor, if not velocity of the air particles, if not velocity of this air column. This air column is moving downwards because velocity of the air particles are v. This air column is made with air particles. Therefore, velocity of this air column is also v down direction. Right? V down direction. Then I can think about air column. Now only whatever I taught in this here, whatever I taught in here must be important hereafter only. Just think about air column. If I erase it, yes. If I consider air column, if I consider air column, when t equals 0, when t equals 0, what can you say about the velocity of the air column? 0. When t equals 0, velocity of this air column is 0. Velocity is 0, u is 0. Right? When the time is simple t, what is the velocity of the air column? Velocity of the air column will be, when the time is simple t, velocity of the air column will be v. Right? I want to find this v only. V. Right? Now, what happened? What happened to the air column? If I say mass of the air column as simple limb, mass of the air column as simple limb, what happened to the air column? Initial momentum of the air column is 0 because velocity is 0. Initial momentum is 0. Final momentum is v. Momentum of this air column is changed in down direction. What is Newton's second law? When there is a resultant force acting on a system, momentum changes. What is the opposite of that? If momentum changes, there must be a resultant force acting on the air column. Linear momentum of this air column has changed. That means there must be resultant force acting on the air column down direction. My target is finding the resultant force Fh. My target is finding this resultant force Fh. Okay. Then we know that the external force equals what? External force equals rate of change in linear momentum. Explained. External force acting on the system equals rate of change in linear momentum delta P over delta T. That means external force acting on the air column is now Fh. Fh my external force. It's somewhat complex question, but it's a very good question. You can get plenty of knowledge. Delta P, final velocity minus initial velocity. Final velocity is mv. Initial velocity is 0. Therefore, I can say final velocity is simple m into v. Time is simple t. Time is simple t. I don't know m, v, time is simple t. Right? I want to find v. The mass of the air column. They have given density of the air column. They have given density of the air column. I want to find the mass of the air column. Then I know that mass means we know there's an equation. Mass means volume into density. Mass over volume. Mass equals volume into density. Mass over volume is density. Mass means volume into density. One equation. Then I can write down mass means volume density of this air column is rho. I say this as equation 2. It's my equation 2. A volume. As you know, this air column is cylindrical volume. I can write down cylindrical volume. Area into height, H, A. How do you find the A? Area is a circular area. What is the equation to find circular area? Phi r squared. And then I can write down cylindrical volume as how? Circular area into height. That means phi r squared into which? I can write down volume. V means phi r squared. Phi r squared into height simple h. Equation 3. This is the difficult part in this paper. Remaining are not difficult. This is the really difficult. Simple B section is difficult. Then remaining is not that much difficult, right? So then I know equation 1 h equals equation 1. I know simple h equals a v simple t. Equation 1. From equation 1, 2, 3, I can write down simple m means a v rho. V means phi r squared h. H means vt. Here sometimes you might misunderstand volume and velocity. So I put volume as v1. Volume as v1. Volume as v1. V means velocity. V means velocity. Then I can write down simple lim means. Simple lim means. Look here, simple lim means I can write down. V1 means phi r squared h. H means vt. So therefore I can write down simple lim means Fh equals. Fh equals. Fh equals. Simple lim. Simple lim is what? Simple lim means v1 rho. V1 means phi r squared h. Phi r squared. Phi r squared. H means vt. H means vt. Phi r squared. H means vt. V1 rho. Density rho. V over t. V over t. Time cancel out. Then I can write down the resultant force acting on the air column downward direction. Fh equals. Fh equals. Fh equals. Phi r squared rho v squared. Now I know phi, I know r, I know rho. Given data. Phi r squared rho, I want to find v squared. Right. This is my equation 1. So the equation simple. This is my very important equation simple. Now they mention in the Roman number 1, they mention calculate the minimum speed at which the rotor must transmit the airflow downwards for the helicopter to barely lift off the ground. Now helicopter is lifting barely. What is the requirement? If they mentioned an object is barely lifting, resultant force is zero on the system, right? Now, in order to lift this helicopter, for an example, let's say now there's a weight, there's a mass, weight of that mass is I say 50 newtons. If you want to lift that mass, at least you want to provide 50 newton. At least if you can provide 50 newton only, you can barely lift that mass. If you are providing 40 newton or 30 newton, you are not able to lift that mass. But if you are providing more than 50 newton, obviously you can lift the mass with an acceleration. You have to understand barely lift off means we provide a force that is sufficient to, that is equal to weight. Now they mentioned this helicopter is lifting barely. How many forces acting on the helicopter? There are two forces. Weight of the helicopter, capital Mg, upward force exerted by this air column, Fh. Now they mentioned helicopter is lifted barely. What can we say about the Fh and Mg? That a vertical force exerted on the helicopter is just equal to weight. Do you understand? Helicopter barely lifts. To barely lift off the ground. To barely lift off. To barely lift off. To barely lift off. What is the requirement? Fh must be equal to. Fh must be equal to Mg. These are the two important things. Equation simple B. Now you can do it hereafter. Simple B. And now they are asking us to find V from equation 1 and 2. I can say Fh equals me. If I consider it by considering the air column, I obtain an equation for Fh that is phi r squared rho V squared. By considering helicopter under the condition of barely lift off, I obtained Fh equals capital Mg. I can equate simple A and simple B. If I equate simple A and simple B, I can write down phi r squared rho capital V squared equals capital M. Now I know capital M, I know G, I know rho, I know R, I know phi. If I subject V, I will get the answer. If I subject V, I will subject here. I subject here. Right. If I subject V, I am getting V equals capital Mg over phi r squared rho whole root. If I substitute V equals capital M is 3600 into G is 10. They asked us to consider phi as 3. Capital R means 5 meters, length of the rotor, phi squared. Density is 1.2 whole root. Then I can write down capital V equals 20 ms minus 1. Then I found the answer for Roman question number 4. Simple B, Roman number 1. Now Roman number 2. right? Now Roman number 2. Roman number 2 says what? It says that find the minimum power required to transmit the air column downwards. Find the minimum power required to transmit the air column downwards. What is the force exerted on the air column? When I consider air column, force exerted on the air column is Fh. What is the velocity of the air column? V. They are asking the power on of this air column. What is the equation? We know power. In work energy power, we know that power equals force into velocity. Power equals force into velocity equation. It's an important equation. Then I want to find the power. If I want to find the power equals force is a what? Fh. Force is Fh. What is the value of Fh? Fh means I told you that 5r squared rho v squared. If not, Fh equals mg. Capital Mg. 3600 is 10. Now you can substitute Fh as 5r squared rho v squared and you can do it. If not, Fh means mg and you can get it. I use Fh equals mg and I will do it. Mg is 3600, g is 10, velocity I obtained as 20. Then I am getting my power as capital P as capital P equals I am getting 720 kilowatts. 720 kilowatts. Then Roman number 3. Roman number 3. What is the velocity with which the air must transmit downwards to make the helicopter move vertically upward the acceleration 2.1 ms minus 2? Now, this is also important point. Now, what would happen when the rotor increases the speed? Now, initially we found the velocity of the rotor as 20 ms minus 1 to barely lift off the helicopter. Right, when the velocity of the rotor is 20 ms minus 1, that vertical upward force is how much? Exactly equal to the weight of the helicopter. Now this vertical, this Fh force, if this Fh force depends on the velocity of the rotor. Look here, Fh equals 5, R means radius of the rotor, we can't change radius of the length of the rotor, we can't change. Density of the air in the ground level, we can't change the density of the air also, but we can change the velocity of the rotor. What would happen if I increase the velocity of the rotor? Fh also increases. Fh also increases. Do you understand? Fh also increases. And now, when the velocity of the rotor is 20, Fh is just equal to mg. There are also resultant force acting on the helicopter. If I want to accelerate the helicopter upward direction with an acceleration, there must be a resultant force acting on the helicopter upwards. Then mg is always a constant. Therefore, Fh must be greater now. How we increase vertical upward force Fh? By increasing the velocity. They are asking, what is the velocity? What is the velocity? What is the velocity with which the air must transmit downwards to make the helicopter move vertically upward? Then acceleration 2.5. Now I consider helicopter and I apply F equals ma. If I consider helicopter and if I apply F equals ma, upward direction, helicopter upward direction F equals ma. There are two forces acting on the helicopter, Fh upwards and weight downwards. Right? Fh upwards minus weight is capital M, the down direction. Mass of the helicopter capital M, acceleration is they have given 2.1. Fh means I can write down Fh as 5r squared rho v squared. Fh means I can write down 5 r squared rho v squared. Now I want to find now v, the velocity of the rotor which accelerate the helicopter upwards with the acceleration of 2.1 ms minus 2 minus mg that side plus mg, therefore mg plus c, mg plus c. If I substitute capital V, if I substitute capital V equals exactly, capital V equals capital M G plus A over pi r square rho whole. When we substitute this one, if we substitute the values, capital M means 3600, G plus A, G is 10, acceleration is 2.1 over 5 means 3, capital R means 5 squared, rho means 1.2 whole root. We are getting our now velocity should be 22 ms minus 1, right? If you rotate the rotor with 20 ms minus 1, that Fh is equal to Ng, therefore helicopter is barely lifted. But if you increase the rotor speed to 22 ms minus 1, helicopter is accelerating upward direction with 2.1 ms minus 2. Fh is increasing with the rotor speed. Fh is increasing. That's the important point. Consider a case where the rotor speed remains constant and the helicopter accelerates. Explain whether the acceleration remains the same as it moves up. Now, this is also important thing. Now, understand now. Normally, with the altitude, density of the air decreases. Very important point. Understand, with the altitude, more we go up, lesser air density. With the altitude, density of the air decreases. Then, when rho decreases, what will happen? When rho decreases, what will happen? When rho decreases, what can you say? Even though you maintain same velocity, when rho decreases, your acceleration decreases. That's what you want to write in Roman number 4. Then this is the important part in this paper. The main important part that I want to teach you is this one. I hope you understood what's happening in this scenario. Right. Now see. Now see, consider a case where the helicopter is moving horizontally forward with an acceleration simply. An object of mass simple limb is suspended from the roof of a helicopter by a long string simple limb. At this instance, write down an expression for the angle of string makes it vertical in terms of A and G. And that one is not difficult. It's easy. It's easy. If I erase it, right. I hope you guys are getting very good knowledge from this. Now this time, simple C part, simple C and simple D. Simple C. Simple C part. Now helicopter is accelerating, not vertically upward. This time helicopter is accelerating horizontally forward direction. Helicopter is accelerating horizontally forward direction. Accelerating horizontally forward direction. Okay. Right. Acceleration is how much? Simply. Acceleration is simply. Simply. Then they mentioned a mass simple limb is suspended from a string of length simple limb. But you want to understand when the helicopter is accelerating forward direction simply, if a mass is suspended from a string, that string is inclined, right? Inclined in this way. It is inclined this way. The string is inclined this way. Am I correct? This one's mass, let's say, simple limb. Mass, let's say, simple limb. Then shall we mark the forces? The first important point is this simple limb mass is suspended to the helicopter. Whatever the acceleration obtained by the helicopter must be obtained by simple limb mass also, one condition. Do you understand? Acceleration of this simple limb mass also to the right side direction simple limb. That's one important condition. If I mark the forces, weight force acting down direction simple limb G, tension force acting on string capital T. Let's say inclination is theta. Inclination theta, this angle will be theta. Am I correct? That angle will be theta. Now, first of all, you want to understand why this mass, this string is inclined. If the string is vertical, understand. If the string is vertical, tension and mg both are vertically active. But we know that whatever the acceleration obtained by the helicopter must be obtained by the mass also. If the string is vertical, mass cannot. Now, if mass is to be accelerated, there must be a resultant force on the mass horizontal direction, right? There must be a resultant force on the mass horizontal direction because direction of the acceleration is horizontally. This mass must accelerate horizontally. If the string is vertical, force acting on the mass is always vertical. Then there won't be any resultant force horizontal direction. That's why string becomes inclined. Then mass can obtain a resultant force horizontal direction. Do you understand? So what is the resultant force acting on the mass in horizontal direction? If I resolve tension into two perpendicular components, T cos theta upward direction, T sin theta downward direction. The resultant horizontal force acting on simply mass is T sin theta. This one is T cos theta, right? In the summary is simple limb mass accelerating to the horizontal direction with simple acceleration due to resultant force T sin theta acting horizontally on the mass simple limb. Therefore, I can consider simple limb man right side direction I can apply F equals M. Right side direction I can apply F equals M. F equals M. Then F resultant horizontal force T sin theta. T sin theta. T sin theta equals simple limb, simply equation 1. And we know the simple limb mass is not moving vertically upwards. Then we can say simple limb mass is under vertical equilibrium. Therefore, I can say T cos theta is equal to mg. Considering vertical equilibrium. Considering vertical equilibrium, I can say that T cos theta equals mg. Equation 2. Then if I divide equation 1 by 2, I am getting. If I divide equation 1 by 2, I am getting T sin theta over T cos theta. T sin theta over T cos theta equals MA over mg. T cancel out, sin theta over cos theta means tan theta equals A over G. Then theta will be tan inverse A over G. That's it. The last section simple D. Last section simple D. Consider a moment when the helicopter is flying horizontally with a uniform velocity of 10 ms minus 1, 2 kilometers above the ground. Then an object is gently dropped. By the helicopter. After 10 seconds from the moment of release, the object explodes into two parts and one part falls vertically down to the place where the explosion took place. Now here you want to assume that mass breaks into two equal parts. If not, we can't do the question. You want to assume that mass breaks into two equal parts. If not, you can't do the question. After the explosion, both pieces fell to the ground at the same time. If I do this, next question I can quickly explain. Next question. Right. If I draw the diagram. Okay. Now helicopter. Right. If I draw the diagram here, I erase this one. Consider the moment when the helicopter is flying with uniform velocity of 10 meters minus 1. Now helicopter is flying with a uniform velocity. Okay, uniform velocity 10 meters minus 1. 10 meters minus 1. 2 kilometer above the ground. 2 kilometer above the ground. 2 kilometer above the ground. Okay, two kilometers. That means 2000 meters. Right. Then an object is gently dropped by the helicopter. Let's say simple m mass is dropped by the helicopter. Simple m. But you must understand what can you say about the initial velocity of the helicopter? Initial velocity of the simple M mass equals to the velocity of the helicopter. The simple M mass is also having a velocity 10 ms minus 1 horizontal direction. That is first important thing. If I ask you what can you say about the vertical velocity component? Vertical velocity component will be 0. 0. Okay, 0. Right. When t equals 0. When t equals 0, I say this point as point capital A. So this point initial when t equals 0, position of the simple M mass is capital A position. Capital A position. Now what can you say about the motion of simple M mass? Simple M mass moves in a projectile motion. Projectile motion. Simple M mass moves in a projectile motion. Give me a second. Give me a second. When t equals 0, velocity of simple mass is horizontal direction 10 m is minus 1. Initial horizontal velocity is 10 m is minus 1. Initial vertical velocity is 0. After 10 seconds later, when the time is simple t, when the time is simple t, let's say simple mass is somewhere here. Simple mass somewhere here. Right? Simple m is somewhere. Now, when the time is simple t, simple limb breaks into two. Okay, we'll talk about that. When the time is simple t, the time is simple t. Time is simple t. Sorry, now the time is 10 seconds. 10 seconds. Now, Roman number one, they are asking what is the horizontal velocity of the object 10 seconds after it is released. When the time is 10 seconds, what is the horizontal velocity of the object? Projectile motion's first important point is throughout the projectile motion, horizontal velocity component remains constant. Initial horizontal velocity component is 10 ms minus 1. Even after time is 10 seconds, horizontal velocity component is 10 ms minus 1. 10 ms minus 1. 10 ms minus 1. Right? So therefore, Roman number one, what is the horizontal velocity of the object 10 seconds after it is released? 10 ms minus 1. Roman number one answer is 10 ms minus 1. Roman number two, what is the vertical velocity of the object just before the explosion? Now I want to find the vertical velocity of the object at the 10 second. Just before the explosion, I want to find the vertical velocity of the object. I say it is V naught. Vertical velocity of the object just before the explosion, I say it's V naught. Now I want to find V naught. I consider equivalent vertical motion from A to B. This point is, I say, point B. From A to B, if I consider equivalent vertical motion. From A to B, if I consider equivalent vertical motion. From A to B, if we consider equivalent vertical motion. Equivalent vertical motion. Downward direction I can apply. Now I know U. I know acceleration is gravitational acceleration. When the time is 10 seconds, I know time. I can use V equals U plus AT equation, right? Down direction. I can apply V equals U plus AT equation. V equals U plus AT equation. What's my V? Final velocity, vertical velocity. Now I considered equivalent vertical motion. Don't confuse with the equivalent horizontal motion and projectile motion. If I consider projectile motion from A to B, if I consider equivalent vertical motion, equivalent vertical motion, downward direction, final velocity is VO. VO, initial vertical velocity is 0, acceleration A is gravitational acceleration 10, time taken is 10 seconds. Then I am getting 100 ms minus 1. That is my vertical velocity of the object just before the explosion. Roman number 2. Roman number 2. Roman number 2. Right? Right? Then, right, very careful listen. Now what happens? An object is gently dropped from the helicopter. After 10 seconds from the moment of release, the object explodes into two parts and one part falls vertically downward to the place where the explosion took place. Now just before the explosion, this is just before the explosion, right? If I draw just after explosion, just before, for your understanding, if I draw here, just before the explosion, just before the explosion, Horizontal velocity component of simple M mass is 10 m s minus 1. Vertical velocity of simple M mass is 100 m s minus 1 just before. Mass is simple M before. Now this simple M mass breaks into two, but some people argue that why they haven't given they are equal, but we have to consider they are equal. If not, we can't do the question. So if we consider these two masses are equal, breaks into two submasses. Each is having I say m over 2 equal mass, m over 2, m over 2. Now they mentioned one mass is, I say this mass is mass capital P, this mass is mass capital Q. One mass is moving vertical down. They mentioned one mass is moving vertical down direction with a velocity of I say v1, v1, right? Then if this mass is moving vertical downwards, before system, after system, this one is only having vertical velocity. But when you consider before system, it is having horizontal velocity. Therefore, Q mass should have some kind of horizontal velocity. I say that's v3. And also this Q mass is also falling down. It is also having some kind of velocity. I say it's v2. Okay, before and after, before and after, before and after. Roman number 3, they are asking find the vertical velocities of the fragment after the explosion. Vertical velocities of the fragment. Vertical velocities v1 and v2 after the explosion. Now, how we come to the conclusion? How we now? They mention in the question clearly. Last statement: both pieces fell to the ground at the same time. Both pieces fell to the ground at the same time. Then what can we say about the velocities of the fragment P and Q? Vertical. I'm asking what can you say about the vertical velocities of the fragment P and Q after the explosion? V1, V2 must be equal. Then only they can fall into the now. If you throw two objects with same speed only, they will hit the ground at the same time. Therefore, understand V1 and V2 must be equal. Then only they can fall at the same time. Therefore, V1 and V2 equal. Now, V1 and V2 equal. Now, I want to find V1 or V2. They are equal. I can apply conservation of linear momentum on direction before and after system. Roman number 3. Roman number 3. If I apply conservation of what? Conservation of linear momentum down direction. Conservation of linear momentum down direction. Before I'm talking about vertical direction, right? Conservation of linear momentum vertical direction, downward direction, right? Before explosion systems, vertical momentum is, I'm talking about vertical momentum, not horizontal. I'm talking about vertical momentum. M into 100 downwards. M into 100 equals after vertical momentum is m over 2 v1. Now I told you v1 v2 both are equal. M over 2 v1, I told you v1 v2 both are equal, plus again m over 2 v1, because v2 also equal to v1 plus m over 2 v1 plus m over 2 v1. If I substitute v1, I am getting my v1 equals my v1 equals my v1 exactly equals 100 ms minus 1. If I simplify this, I'm getting v1 is exactly equal to, just cut all simple terms, 100 ms minus 1. That's it. Then I found Roman number 3 as well. Roman number 4, find the vertical velocity. Okay, Roman number 3, find the vertical velocities of the fragment after the explosion. V1, V2 both are equal. Vertical velocity is equal. 100, 100. Find the horizontal velocities of the fragment after the explosion. First, P fragment does not have any horizontal velocity component. Why? They mentioned clearly P is vertically falling down. So therefore, Q only having some kind of horizontal velocity component V3. I want to find V3. Again, I apply conservation of linear momentum, horizontal direction. Round number 4. Again, I'm applying conservation of linear momentum, horizontal direction. This direction, conservation of linear momentum. Then what can you say? Because we know that vertical components do not contribute for the linear momentum by each. If I consider horizontal direction, conservation of linear momentum, before explosion, system's horizontal linear momentum is m into 10. M into 10 must be equal to, now P does not have any horizontal linear momentum because P does not have any horizontal velocity, but Q is having horizontal velocity. Horizontal linear momentum of Q is m over 2 into V3. 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 If I subject V3, I am getting V3 equals how much? 20 ms minus 1. V3 equals I am getting 20 ms minus 1. The Roman number 5. That's the last one. Then this question number 4, the largest. I think we have taken nearly. I think we started at 750. We have taken 15, 9, more than 1.5 hours to discuss this question number 4. Very good question. Find the distance between the 2 points where the pieces land. Okay, now I understand. I found the values V1, V2, V3. Now it breaks into two fragments. It breaks into two fragments, right? 100 ms minus 1 vertical breaks into two fragments. Breaks into two fragments. Capital P and capital Q. This is Q. This is P. Capital P is moving vertical downwards. Capital P is moving vertical downwards. Am I correct? Capital P is moving vertical downwards. Capital Q has horizontal velocity component V3 20 ms minus 1, vertical velocity component V2 100. Therefore, capital Q is moving in a projectile motion. 20 ms minus 1, vertical one is 100 ms minus 1. So therefore, Q is moving in projectile motion. You got it? So they are asking the gap between them. Capital P will incident at this point. Capital Q will incident on the ground at this point. So I want to find the capital R range. Capital R. This is my target. I want to find capital R. Then I consider, if I consider capital Q, if I consider equal horizontal motion, if I apply C equals UT, I can get the answer. But before that, I want to find this vertical distance. I should find this vertical distance before. Therefore, I consider A to be vertical motion. If I consider A to be projectile motion, I consider equivalent vertical motion. If I consider A to be projectile motion, right? If I consider A to be, equivalent vertical motion, equivalent vertical motion, equivalent vertical motion. If I apply downward direction, S equals ut plus half at square. Downward direction, if I apply S equals ut plus half at square, I can find this vertical displacement because what is S? From the point of release to the point of explosion, vertical displacement I can write as u is 0, half, acceleration is 10, time taken is 10 seconds, A to B time is 10 seconds, 10 square. Then I am getting 500 meters. 500 meters. The vertical displacement from the point of release to the point of explosion is 500 meters. Then we can say from B to C, If I consider B to C projectile motion, this one's projectile motion, vertical displacement is B to vertical displacement is 1500 meters. This one is 1500 meters. Okay. Now I consider B to C projectile motion. Considering Q particle, Q fragment, if I consider B to C projectile motion, equivalent horizontal motion, if I consider, now I want to find capital R because horizontal displacement done by the Q, that is the gap between P and Q when they land. When they land, equal horizontal motion, only equation we apply is S equals ut. S equals ut. What is my S? Capital R. I want to find this capital R. I want to find capital R. What's my U? My U will be 20. Velocity of the horizontal velocity of Q will be 20. 20 time. Simple T will be, I don't know. Time taken for this Q particle to move from B to C is I don't know. Simple T. If I can find simple T, problem solved. I consider equivalent vertical motion from B to C, considering Q particle, equivalent vertical motion. If I consider equivalent vertical motion, downward direction I apply S equals ut plus half AT square. Downward direction S equals ut plus half AT square. From B to C, if I consider equivalent vertical motion, vertical displacement is 1500. 1500. Vertical velocity, initial vertical velocity is 100. Q particle, initial vertical velocity is 100. Time is simple T. I want to find simple T, then only I can find capital R. Simple T uh, plus half into 10 T squared. If I simplify this, I am getting my simple T as, if you simplify this quadratic equation, we are getting our simple T as how much? Our simple T will be 10 seconds. Simple T will be 10 seconds. Therefore, this one from equation 1, we can write down R equals 200 meters. From equation 1, I can write down 20 into T means 10, 200 meters. Then that question is entirely completed. Then we have one more essay question. It won't take so much time. We can finish quickly. It won't take so much time. Right. We'll take a small break. So we'll take a small break. Yes. Then we can finish it today. Now 9:50. We'll take a small break. Right. You have to listen. Right. Okay. We start. Okay, we start. Now, question number 3. Doppler effect is when there's a relative motion between source and the observer towards or from each other. The observer observes a different frequency. Now, first you want to understand Doppler effect means when there's a relative motion between source and observer. If there's a relative motion between source and observer, there is a difference in actual frequency of the source and apparent frequency heard by the observer. Just think about a speaker of frequency 500 hertz reaching towards you, but you are stationary. You don't hear the frequency of the sound as 500 hertz. You hear somewhat different value. The change occurring in the frequency. That's what we call as Doppler effect. Okay. Now, three simply Roman number 1, name the type of waves according to the direction of vibration of the wave particles. We can divide waves into two main segments, transverse waves and longitudinal waves based on the particle vibration. If the medium particles are vibrating perpendicular to the direction of wave propagation, that's what we call as transverse waves. I told these things, transverse waves. Question number 3, simply. Question number 3, simply. Roman number 1. Now we can divide waves into two. Now they're asking name the types of waves according to the direction of vibration of the wave particles. Then we can divide waves into two segments, transverse waves and longitudinal waves. Transverse and longitudinal waves. Longitudinal waves. Now what is the depend based on the direction of wave propagation? Suppose medium particles vibrate perpendicular to the wave propagation. Let's say this arrow represents the wave propagation. Wave propagation. If the medium particles vibrate perpendicular to the wave propagation, this is what this type of waves we call as transverse. Example, water waves, electromagnetic waves, water waves, electromagnetic waves. Those are the examples, right? Okay. Then next example, next type of waves, longitudinal waves. What is the difference? What is the longitudinal waves main characteristic? Direction of wave propagation and direction of medium particle vibration are parallel. right? Medium particles vibrate if it move back and forth in the direction of wave propagation. The wave propagation is also to the right side direction. Wave propagation also this direction. Medium particles also vibrate parallel to the wave propagation. This is what we call as longitudinal waves. Example is sound waves. Then Roman number 2 give two examples where Doppler effect does not occur even if there is relative motion between the source and the observer. Now this is very important point. Now first instance is I explained that suppose if the observer or source perpendicular to the line connecting observer and source. Let's say this is my observer for an example, right? My source. It's my source. If the source is moving perpendicular, if the source is moving, it can be a source or observer relative to the observer or source. Now I considered source is moving relative to the observer perpendicular to the line connecting source and the observer. In this type of examples, understand actual frequency of the source and actual frequency of the now there's kind of relative motion between them. But in this instant, actual frequency of the source and apparent frequency of the source are same. That means there is no Doppler effect occurring in this instant. Do you understand? That is one important instant. If the source or observer perpendicular to the line connecting source and observer, that instant Doppler effect won't occur. Do you understand? That instant there is no frequency difference. Whatever the frequency released by the source, same frequency is heard by the observer. And next instant is supersonic speeds. If the source or velocity of the observer larger than the velocity of the wave. Suppose if the velocity of the source or observer larger than the velocity of the wave, at that instant also Doppler effect won't occur. Next one is now this is somewhat important thing today. Today question also we have to deal with some important point. Next one is just think about a kind of source is moving towards stationary observer. Now source is moving towards stationary observer. Even though now just assume when the source is exactly at the same point where the observer is also exist. Just think that now this vehicle is coming towards the stationary observer. Then exactly the particular instant, vehicle and source and observer both are at the same point. Do you understand? Exactly at the point, both the source and the observer both are at the particular. Now, what I want to say is, source is moving towards the observer at a particular instant. Source and observer both are at the same point. At that instant also, even though there is a relative motion between them, Doppler effect won't occur. So these are important points. The first important point is when velocity of the source or observer is perpendicular to the line connecting source and observer, Doppler effect won't occur. If the velocity of source observer are greater than the velocity of the waves, sound waves or whatever, Doppler effect won't occur. Even though there's a relative motion between the source and observer, if the source is exactly at the observer at that instant, Doppler effect won't occur. So then they have given a table. Copy the following chart. Your answer sheet mention how Doppler effect occurs in the following instances. Uh, Now they have given three columns: velocity of wave relative to the observer. Now, very important point to understand. Now, just think about, for an example, just think about sound waves. Doppler effect occurs on sound waves. Now, do you think sound wave velocity changes? Do you think velocity of the sound wave changes due to the velocities of source and observer? No. But someone can impact, very careful understand, someone can impact velocity of sound relative to the observer. We learned in the theory class. Who is that someone? That someone is wind. Based on the direction of wind, velocity of the sound wave can be changed relative to the observer. Now, but in this question, they don't talk about any wind or anything. Therefore, understand velocity of the wave, velocity of the sound wave related to the observer does not change, remains constant. So in the third column, all the answers should be no change, no change, no change, no, no. Now just think about first row. Now motion of source is away from the observer. Observer is still. If the source is moving away from the observer, stationary observer, what can you say about the apparent frequency? Apparent frequency is getting lower than the actual frequency. Apparent wavelength is larger than the actual frequency. Second case, now source is at rest, observer is moving away from the source. Then apparent frequency lower than the actual frequency. Apparent wavelength larger than the actual frequency. Third one, source is moving towards stationary observer. Apparent frequency is larger than actual frequency. Apparent wavelength smaller than actual wavelength. Fourth one, uh, so observer is moving towards stationary source. Then also apparent frequency larger, apparent wavelength smaller. If both are moving away, apparent frequency smaller, apparent wavelength larger. Small thing, right? Then the last section, the last section, right? Last section. An ambulance is moving towards a mountain at a velocity UA, sounding a siren of frequency F naught. A motor car with a velocity of UM is following the ambulance. Okay. But the last important thing, I think we can finish the class within 15 minutes. I think so. Right? I think so. Okay. Now, simple B. Simple B. Simple B, Roman number 1. Ambulance is moving towards a mountain at a velocity UV. Ambulance, mountain, velocity UV. Okay. Mountain. Mountain, capital name. Ambulance. The ambulance. Ambulance. Ambulance, capital E. Give me a second. Right. That's a motor car. Velocity of the ambulance is UA. UA for velocity of ambulance UV. And there's a motor car. There's a motor car. Motor car. So I say velocity of the motor car is mountain motor car with a velocity of UM. This is UM. Motor car is UM. Right. Ambulance is moving towards the mountain at a velocity of UA, sounding a siren of frequency F naught. Now this ambulance is sounding a siren. Actual frequency of the siren, actual frequency of the sound emitted from the siren is F naught. Actual frequency of the sound emitted by the ambulance is F naught. You want to understand sound emitted by the siren spread through all the region, right? When we consider this motor car hears, different motor car receives sound emitted by the siren in two different ways. That's the important thing in the question. Motor car means sound emitted by the siren received to motor car in two different ways. Different motor car hears sound emitted by the siren in two different ways. First way is directly from the ambulance. Motor car hears siren sound directly from the ambulance. That is first way. Second way is sound emitted by the siren incident on the mountain and reflected back and it reaches the car. There are two ways. The two sound waves received towards the motor car. From motor car receives two different sound waves. Okay, that's the idea. Now derive an expression for the apparent frequency F1 of the siren perceived by the driver of the motor car using UA, UM and VF0. Now, I want to find apparent frequency of the sound wave heard by the sound wave heard by the motor car directly from the ambulance. Then this time, who is my source? Ambulance is my source. My source will be ambulance. Who is my observer? My observer will be car, motor car, motor car. Then, what can you say? What type of relative motion that they move? Ambulance move direction. Ambulance and motor car, both of them moving in the same direction, but car is behind the ambulance. So what is the equation? F dash apparent frequency heard by the motor car F dash equals V over V. I think right. Now numerator there is observer. Then observer is car. Then if I assume ambulance is stationary, car is moving towards stationary observer. Sorry, car is moving towards stationary ambulance. If I assume ambulance stationary, car is moving towards the stationary ambulance. That means observer is moving towards the stationary ambulance, V plus V naught. And if the denominator represents source, if I assume that car is stationary, ambulance moving away from the car, that means the source is moving away from the observer, V plus Vs into V is the equation, right? Now, if we substitute, they are asking F dash in terms of now F1. I want to find F1. So F1 equals apparent frequency heard by the motor car equals velocity of the sound wave is V, velocity of the observer, motor car is UM over velocity of the source, that means ambulance, UA into simple F naught, simple F. Actual frequency is F naught. Is the answer. Is the answer. right? Then Roman number 2, if the siren sounds, the ambulance reflect after hitting the mountain. See, now I told you before that this motor car hears two sounds of the siren. First sound is directly comes from the siren. Second sound incident on the mountain and reflected back and reaches the motor car. So therefore, they are asking if the siren sound of the ambulance reflects after hitting the mountain. Derive an expression for the apparent frequency F2 the driver of motor car perceives using UA, UM, VN. It's not F2, it must be F naught. UA, UM, VN, it must be F naught, not F2, right? Then Roman number 1, Roman number 2. So I can consider this Roman number 2 in two different stages. If I consider Roman number 2 in two different stages, Roman number 2 in two different stages. First of all, we'll consider ambulance and mounting. If I consider ambulance and mounting, right? Stage 1. Ambulance, mounting. Ambulance, mounting. Now, who is my source? Ambulance is my source. Mountain is my observer. Then actual frequency of the source is if not, if observer is the mountain, if you assume observer is your mountain, apparent frequency heard by the mountain is, I say, F dash, right? Then velocity of the ambulance, we know that's UA. It seems like stationary observer moving source. Source is moving towards stationary observer. Then I can write an equation for F dash. F dash equals V over stationary observer moving source. V minus V is simple if. I think you guys know how this came. That means F dash equals V over V minus UA F naught. Equation 1. So I see this is my equation 1. This will be my equation 2. Now, what would happen after the sound waves incident on the mountain? After the sound waves incident on the mountain, what would happen? They reflect back with the same frequency F dash. They reflect back with the same frequency F dash. That reflected sound waves reach the car. The reflected sound waves reach the car. I draw that one as my stage 2. I draw that one as my stage 2. Stage 2. Right? Stage 2. Now, mountain reflects the sound waves with the frequency of F dash. That sound waves, reflected sound waves, reaches the motor car. That apparent frequency heard by the motor car is F2. Velocity of the motor car is UM. Now, this time, who is your observer? Who is your source? Now, it seems like now the sound waves are reflected from the mountain, but it seems like mountain is emitting sound waves. Therefore, we say that this mountain as our source, motor car. This motor car is our observer. Stationary source moving observer towards the stationary source. Then equation for apparent frequency F dash equals V over V plus, sorry, V plus V naught. Observer is moving towards stationary source. VF. So therefore I can write down F dash means F2 apparent frequency heard by the observer is F2. equals to V plus V naught. V naught means velocity of the source, that is UM, over capital V, the actual frequency of the source. Actual frequency of the source is mountain's frequency F dash. F dash. F dash. This will be my equation 2. From equation 1, equation 3. From equation 3 and 2, I can write down. From equation 3 and 2, I can write down what? I can write down F2 equals. From equation 2 and 3, I can write down F2 equals. F2 equals V plus U capital M over V. F dash means V over V minus UA into F naught. We cancel out. We are getting F2 equals. We are getting F2 exactly equals. F2 exactly equals V plus U capital M over V minus U capital A into F naught. That's the answer. Then Roman number 3, if we substitute these values. Roman number 3, if we substitute these values, if we substitute 144 kilometers per hour, if we convert to meters per second. Now they are asking F1, F2 values. F1, F2. We know the equation for F1, F2. The Roman number 3, F1 will be, if I convert 144 kilometers per hour to meters per second, it will become 40 ms minus 1. It is 40. Then B is 340. This is 40 over 340. This is 20, right? Velocity of the motor car is 20. This is 40. 1500. Then we are getting the answer as F1 as F1 will be 1421.05. 1421.05. 1421.05 hertz. Because 72 kilometers per hour means 20 ms minus 1, because you convert, how do you convert kilometers per hour to meters per second? 72 5 over 18. That means 20 ms minus 1. 144 kilometers per hour means 40 ms minus 1. Just do it, then you will understand. Therefore, F2, if you substitute it, F2 will be 340, UM is 20, 340 minus 40, 1500. Then you are getting my F2 value as, how much? 1800 hertz. Right. Then we have one last part, simple C. We'll discuss simple C in different video. Okay. We'll stop for now, 10:30.